Okay, we begin lecture 3. Quick summary of the key points that we had discussed in the last lecture. We had talked about the aspects of the different forms of multiple access: time division multiple access, frequency division multiple access, code division, and orthogonal frequency division. I would like to encourage you to think about not narrowband systems, but think about a broadband system which tries to achieve of the order of 10 megabits per second using a bandwidth of 10 megahertz. How would you handle the different types of users, FDMA or CDMA or TDMA, and what would be the trade-offs? That is something that will help us understand what are some of the advantages and disadvantages, and then get a perspective. Again, the purpose of the first 4 lectures is to give you a bird's eye view of all the different elements of the wireless systems, and then zero in on specific aspects of the wireless channel itself. So let's begin. A quick element about the 4th generation systems. They are using orthogonal frequency division multiple access as the multiple access mechanism. We talked about yesterday the use of smart antennas and the possibility of using frequency division duplex or time division duplex. There was a couple of questions on what is TDD, is one better than the other. The answer is TDD is an option when you don't have much spectrum. You can support both links, both bidirectional links on a single carrier. You share the carrier between the transmission from the base station to the mobile, and then you switch to the other direction. So basically, frequency limited environments, TDD is an option, but FDD is probably easier and more widely deployed around the world. Some more elements of the 4th generation systems, very important, and just make a note of it, because these are things that you will probably, if you're reading current literature, you will find that these are referred to. One is called coordinated multi-point transmission, COMP. CO stands for coordinated MP multi-point transmission, and what it means is that we now have large number of small cells, and very likely there are users who are at the edge of the cell. So you can see on the arrow that is pointing to is on the edge of the cell with the red arrow. The other one is on the edge of the cell for the neighboring one. Now both of these, if the base stations transmit at the same time, the red base station is transmitting to this mobile, but it will interfere with the other, and vice versa. So both mobiles at the boundary are likely to get affected in terms of their ability to receive the signal. However, if the 2 base stations were able to talk to each other and say, okay, now you transmit to your mobile at the boundary, then once you finish, then I will transmit. That's basically coordination of transmission. Now, how is that possible? Because today base stations, many of them are on an optical fiber network, and therefore communications between base stations is very quick, and we can easily do it well in time, so that the transmission to the mobiles can be done without any latency. So this is a very powerful technique which reduces interference without reducing your capacity. So basically you find out which are the mobiles that are at the edge of the cell, and then you do the transmission. Now you can do something even better. We know that using multiple antennas, more antennas, is beneficial for any form of wireless transmission. So the 2 base stations can coordinate and transmit the same information to the mobile, because anyway when this one is transmitting, the other one is not doing anything, so therefore they could transmit. But this will result in a reduction in capacity, because a part of the time when this base station should be transmitting to its own users, it is taking part of its time to transmit to the mobiles in the other neighboring cell. So with the reduction of capacity, if possible, you can get additional benefit, but in any case the important thing is the coordination between the base stations. Okay. Now another element which is very prominent in the 4th generation is the notion of a relay. Now a relay has got several definitions and meanings. The cellular definition of a relay is a node which talks to the base station on one side and to a mobile on the other side. Basically it acts as a link, as an agent which receives and forwards information. It does not do any much processing itself. It enables a connection. the advantage. The mobile has to transmit with only low power because it is transmitting to a node which is geographically very close. The second advantage is that a relay node can typically be larger, can have more antennas, and therefore will have a better path to the macro base station, and therefore there is an advantage there as well. So two types of relays are possible. One is a relay node to extend your coverage. You want to extend your coverage. That is basically the relay node is sitting on the boundary so that it can extend beyond the current boundary. The second one is to provide high data rates to some users. So you're not going outside the boundary, but you want to give better signal to one or two mobiles. So therefore, the relay node will provide high data rates in its vicinity, and that's a second advantage that you get. So relays of two types, the coordinated transmission of two types, and again there are several flavors of it, very useful for us to know. These are all part of the fourth generation systems. Another concept that has become very popular in the fourth generation is the notion of a femtocell. A femtocell is basically a base station that you deploy inside your house for yourself. So in other words, you have to coordinate it with the operator, but this base station is sitting inside your home. So that means all the devices connected to your home will get very good signal. Now, how does the femtocell connect to the cellular network? The assumption is that there is a broadband connection to your home. Now, if you don't have broadband connection, this concept does not work. So you can see that this is a concept that came from the parts of the world where there was very good copper deployment and there was broadband to the home already available. So this is a very attractive concept because then almost every home could have a femtocell, and once you're inside your home, you would get very high data rates. Now, what do we do for the Indian context? Since we don't have this, we'll answer that question. Another aspect of the fourth generation is the recognition that cellular systems are more or less the backbone of communications of countries like India. And we also have to recognize that we don't have a very reliable power system, electrical grid system. So which means that you have to have proper backup for your cellular towers. So the way it works is the cellular tower is there. In order for the cellular tower to operate well, very often they provide air conditioning, so air conditioners are there. Now, if the air conditioner should not fail, this tower should not fail, so therefore you have a diesel generator to back up for both of these. So basically the minute the grid goes down, the diesel generator starts and the site continues to operate like before. So this essentially means that there's a large consumption of diesel, because anytime the power goes down, the diesel generators have to turn on. And about 20% of the cell sites in the country do not have grid power. That means they are running on diesel 24 hours a day. So which also says that there is a huge amount of diesel consumption. After the Indian Railways, cell phone operators are the largest consumers of diesel. So they basically are a huge amount of diesel, and they're not consuming it and storing it, they're actually burning it. So which means that there is a concern about the emissions. So therefore the push in fourth generation says reduce power consumption, reduce wherever we can. They call it green communications, but as a communication engineer, we just we make the note that we have to reduce power wherever we can. So here comes the aspects that we would want to summarize. Relays are very important because especially if you want to achieve speeds like 100 megabits per second, it's good to have a relay close to you so that you can get good connectivity. Now, how does the network create more capacity? The way the network creates more capacity is you initially take a deployment of cells. If you find that there are a large number of users, you create smaller cells within the large cells, call it micro. The bigger ones are called the macro cells. Then you create something which is smaller called micro. Then if you still find that more capacity is needed, you create even smaller cells called pico cells. And then if you're still not satisfied, you as a consumer would go and say, okay, I'm going to create a pico cell, and I will connect to the network through my pico cell. So since you have different size network cells, heterogeneous networks, macro, micro, pico, femto, they are called heterogeneous networks, different sizes, and short form is HETnets. Any literature that you see on 4G will refer to HETnets, and it's very important to know immediately that you're talking about capacity achieving capacity using different size cells, and basically coordination is a very important element. Now, how do we address this in the Indian context? We don't have broadband to the home, but I still would like the femto concept. So this is a concept developed at IIT Madras. This is a concept which says, yes, I will deploy the femto inside the home just like everybody else, but the femto will not be connected on a wired broadband. The femto will actually talk to the base station over the wireless link like a relay. Okay? It's a femto relay hybrid. It talks to the base station like the way a relay does, but its option is only to serve the users within a network, and it is deployed by the user. So this is called a indoor personal relay. It's a femto cell. It's indoor. It's wireless in transmission, and it is for the use of that home. Again, these are some methods and by which we can reduce the energy consumption and improve the coverage of the systems within the homes, and that's an advantage to us. I would like to switch gears a little bit. We've talked a lot of technology. Maybe for those interested in the business angle of it, here is a couple of slides which makes you think about the opportunity that is ahead of us. Indian market summary, population in the vicinity of 1.1 billion people. About 70% of the population still in villages, spread across 6 lakh villages in India. If you look at it in terms of households, number of houses units, around 200 million. You take an average of 5 people per household. Okay? So very large user base is there in India. The factors that affect the Indian market, we have very high user densities in the metros. Mumbai, Delhi, Chennai, so the densities are very, very high. That's why base stations have to be every 200 or 300 meters. But on the other hand, on the rural side, the densities are very sparse. The good thing is we will have an optical fiber grid running across the country called the BharatNet, and broadband for most people is going to be wireless broadband because there is no other form of broadband. So the Indian market places some unique requirements. But why would operators be interested given the fact that it is a low ARPU market? Average revenue per user. It's not a market that will generate a lot of revenue. There's a lot of competition, so prices are low. So why would operators be interested? So in 2010, IIT Madras, along with all the operators listed below, we did just a market analysis, and we led the study. This was to focus on the city of Mumbai. It has about 16 million people, and about 70% of these 16 million people live in the dense parts. That's around 600 square kilometers. And if you assume 5 people per household, you will find that the density of households comes out to 3,733 households per square kilometer. Again, it's a simple calculation, you can do that. Okay? At that time, we said that maybe wired broadband may come in. At that time, we didn't see as far as 2016 or 17. We thought that we'll make a very modest assumption that of the people who are subscribing for broadband, only 50% will be subscribing on wireless. Okay, the rest of it will have to do other forms. So which means that approximately half of that, these are households, mind you, not individuals. So you have to multiply it by 5 if you want to take individuals. So from a household, if you wanted to connect to broadband, there are about 1866 connections per square kilometer. And Mumbai, we assume that approximately the cells would have become small enough that 0.575 kilometers would be the radius. We know that it's now much less. So even with 0.75 kilometer cell radius, there would be about 3,300 subscribers per cell. Okay? Now, if there are 5 operators competing equally, they will have 660 subscribers per operator per cell. And you multiply it across the number of cells which will be in the city of Mumbai, and you can start to see, this is households. You have to multiply the number by 5 if people are starting to also have broadband subscriptions on their phone. So which means that this is a huge market posing some very unique challenges, and that is part of the ongoing discussion. How does India leverage our strengths as a big market? So again, the cellular market is a very, very attractive market. The way it has evolved, even in 2010 people said, it's very, very attractive. Now in 2017 it becomes several times more attractive. Now I want you to take you back to understand how a call on a cell phone network is made. Again, it's a conceptual discussion. As long as you understand the overall flow, I would be very happy. So this is how a GSM network is originally architected. Okay. And again, the details are there for you in the slide, but the concept is what is important. You have the mobile. The mobile talks to a tower. We call that the base station. And behind the base station there is a controller, base station controller. So together they are called the base station subsystem. That's what communicates with you over the wireless link. So that's all the wireless there is in the entire network. Everything else is wired. Behind the base station sits a switch. A switch is something that will direct or route your call. Now supporting the switch are several entities which are needed for a wireless system or a cellular system. The two most important things about a cellular system, one is mobility. The user is not in one location but can move all over the place. So how do you keep track of the user? Mobility management is one of the elements that is needed in a cellular network. The second one is authentication. Now when you have a wired telephone and you pick up the phone, the operator knows that it is you who is calling, and they know who to send the bill to. So there is no doubt about verifying who is making the phone call, but that is not the case in the context of a mobile device, because you may be in in a network far away from home and you want to make a call. Now how does that network know that you are a valid user of your own home network? So basically authentication. To know whether this is a valid user, what is the subscription, can I go ahead and give him an STD call privilege, and all of those. So that is part of it. And calls which you make may go to another user who is within your own network. Then you don't need to go outside the network. The switch will route you back into the network. Occasionally you may go to the network of another operator. So which means that you go through a gateway called PLMN gateway, a public LAN mobile network gateway, that will connect you to another operator, mobile operator. Now occasionally you will call to a landline network, then there is a gateway to the PSTN, public switch telephone network. So basically there is a base station subsystem which talks to the mobile. Behind the base station subsystem there is an entire network of devices that are there to give you mobility, to give you authentication, to give you the connectivity. It's all seamless. They signal very, very fast between each other, and what signaling happens is good for you to know, because occasionally people get very impatient. It's like, oh, why is the call taking so long? Let me explain to you what are some of the reasons why the call is taking so long. Okay, so again, concept. How does a mobile terminated call happen? Let us say, just for example, a landline network, a landline telephone wants to call a mobile. Okay, and you can take mobile to mobile. All of those are good for us. Okay, the assumption is that this is a user who is not in his home network, basically somebody who is registered in Chennai but maybe has gone to Bangalore. But the landline network subscriber does not know that, doesn't dial anything differently, dials the same 10-digit number. So the first step is, step 1, the landline subscriber dials a 10-digit number. The PSTN network looks at the number which is being dialed and recognizes, okay, this is a mobile number, so I need to forward it to the nearest mobile gateway. So step 2, the signaling goes to the mobile gateway saying, okay, there is an incoming call for this number. Now the local mobile, let's say you are a Vodafone subscriber, the gateway then checks with the Vodafone home register. That's basically your home network. Let's say from your number they can figure out that you are a Chennai subscriber. So it comes to the Chennai database and says, okay, validate this, there's an incoming call for this particular subscriber. The database checks the record and says, wait a minute, this user is not here in the Chennai network, he is actually in the Bangalore network. So the database then sends the information to the Bangalore database and says, oh, by the way, is this user currently active? The Bangalore database replies back to the Chennai database saying, yes, this is his current roaming number. Roaming number is like a temporary number that the network has given you. If you use this number, this user will respond. So then the Chennai database informs the gateway saying, look, we cannot terminate the call in Chennai, you need to terminate it in Bangalore. So the call now through signaling goes to the Bangalore switch. The Bangalore switch once again checks with the database, says, okay, I have an incoming call for this mobile with this roaming number. Do you have the details? It checks his database and says, yes, I know where to find this user, and sends him back something called a temporary mobile subscriber identity. And the reason the roaming number is mapped to a temporary identity is a smaller number, and it is something that can be changed for privacy reasons. And so, by the way, this is the area in which I last heard from the subscriber, that is location area identity. This was the last time I connected with this. So the switch then forwards it to the base station subsystem, which is operating in that location area, and says, page the subscriber. The paging goes out to a large number of cells. Whichever cell the user is in, he will respond. The paging stops, and then the information, can you see, goes back to the Bangalore MSC, back to the Chennai MSC, back to the telephone network, and back to a connector thing, all of them before 3 beeps happen. Okay? So all of this has happened. Occasionally, maybe there is a problem with you did not register, or you did not, you moved away from the network, or you switched off your mobile, or put it in airplane mode or something for whatever reason, or it ran out of charge. So at that time the network may not know, so actually tries to page you for some time and then comes back saying, okay, no response. But it is it's quite fascinating how the system has been architected, and all of it to enable mobility and authentication. Why so many handshakes between different registers is because they need to know that that you are a valid user. So the home database is very important. The visitor database is the only one that can provide you the service, and at the end of the day, the base station system and the switch, all of them have to work in harmony. So it's actually, the more you look at it, it's a fascinating system, very well designed, and it is actually very creditable that they have designed a network that today you cannot tell the difference between the calling a landline user and a mobile user. Really takes no difference in time, because the signaling is so fast, and our ability to track the users has also become very good. Before we move on to some other interesting aspects of 4G, I thought I should at least show you what the old phones looked like on the inside. Old phones had a display. So that was the display. As you can see, it was one which probably had 3 or 4 lines, would have a few images to show battery level and network. The keypad basically was on the body of the phone. There was circuitry behind it, so when you pressed it, the certain connections would get energized, and then the device would know what keys were pressed. Now if you remove the keypad, then the insides of the phone. Always good to start with the antenna. Antenna at one end, microphone at the other end. So basically you know which end is which. So your audio signal goes in here, gets processed by the DSP, then gets converted to the intermediate frequency, to the RF frequency, and right here you see some metal shielding. That's the power amplifier. Now why should the power amplifier be at the top? It has to be near the antenna, right? Because that's a logical place. But where is your ear? near the top. So that's why if you talk for very long, your ear gets hot, because you are very close to the power amplifier. So so where should you have put the antenna? Somewhere here, right? put it far away, put it, but people don't like something sticking out, near their mouth. So they said, okay, leave it in the original design. So that's how it was. And of course, there you have more than 70% or 80% of the weight of the phone comes from the battery. The rest of it is very light because the components today it's actually highly integrated. This is an earlier generation phone. Today you will probably see just one chip which operates this plus some analog components. Okay. Very, very quickly, antennas, different types of antennas. This is what's called the stub antenna. There used to be a telescopic antenna. Basically, you could pull it out and then you could communicate and then close it so that you can keep it safe. Otherwise, this was the best antenna that in terms of performance. Why? Because it comes out, and whenever it communicates clear of your head. So basically your head does not act as a obstruction to the signal. So but this was very quickly discontinued. Anybody know why? Anybody can guess why?
Because they break off.
They break off, and why do they break off? People keep pulling it in and out. People don't know what to do with the antenna. They keep playing with it. It breaks and then they come back for warranty. So in Ericsson, they said, change that antenna. We don't want it because it breaks all the time. So, so today, what do? They put the antenna inside. So basically, if you ignore the antenna that's outside, you see the antenna that's inside. This is basically a patch antenna. Now, unfortunately, when you hold it and you keep it against your face, either your hand is absorbing or part of it is absorbing on your face, but that's how the antennas are today. But again, the important thing is to know is how the antenna is and how it works, so good thing. Now, one of the questions that is commonly asked is, okay, will I get cancer? Okay, let me answer that question. It's an important question because we are all users of wireless technology. Maybe a little bit of ethics is also tied to it. One of the requirements in Ericsson, I used to work for Ericsson, and we made cell phones, was that a phone cannot go into the market which you will not give to your wife or child. Okay, so you cannot send a phone out into the market. So the issue of sending an unsafe phone into the market is out of the question from a ethical point of view. But there's also a legal requirement, and let me just mention that. So the effect of electromagnetic radiation on human tissue is measured by something called specific absorption rate, SAR. And there are units of SAR, which either watts per kilogram, or there are different ways of measuring it. And typically, these measuring methods are specified by the different regulatory agencies. The safe limit, that means there is absolutely nothing to worry about radiation if the SAR value is written as 1.6. Okay, in the US, and it is 2.0 in Europe. Now, keep in mind that this already has a significant factor of safety, a factor of 10 safety from the safe limit. So basically, they took the safe limit, applied a factor of 10, and said, okay, there is no way this device is going to cause any damage or radiation hazard. Okay. So, and of course, if you take and look at your SAR values, it will be sometimes mostly less than 1. So, in fact, when we design the phones, we make sure it's even lower than what is allowed. But as a good communications engineer, here are some good points to keep in mind. When does your phone transmit with maximum power? When you are in bad signal. Okay, how will you know whether, I don't know where the cell tower is. I don't have any idea whether the base station is receiving my signal strong or weak. How do I know that?
Voice content, quality of the.
Well, voice quality is somewhat of an indicator, but you may not notice it as easily.
There are towers also in the phone.
Okay, a good indicator is if you see only one bar on your phone, you are not in very good condition. So there's a fair amount of reciprocity in the channel conditions. So move to a different location. if you're inside an elevator in a basement, you can assume that your cell phone is transmitting with maximum power. So again, the good suggestion would be is go to some hands-free mode if you're going to be on a long call, and try to take your call from a place where the signal strength is as good as you can see on your phone, and that's going to mean that your phone will transmit with the least amount of power that it needs to. So again, some common sense tips, but at the end of the day, it's a safe device. Batteries have been one of the mainstay of the phones. We started off with nickel cadmium batteries, then went to nickel metal hydride. Today most of your batteries look like this, lithium ion batteries, and in the future they're talking about some in further enhancements. Maybe it's going to be some fuel cell or something based on solar, but as of now it's lithium ion. And how do we characterize a battery? Batteries are characterized by means of a parameter called milliampere hour, and it's not by coulombs or by the charge it holds. That's because the battery voltage is standardized. So 3.7 volts is standard. So if you can, whatever amperes you can draw at 3.7 volts for the number of hours, that gives you the charge that your battery holds. So most of the time batteries are rated as 2700 milliampere hours or 3000 milliampere hours, and it's good to see that. And the understanding of it is a 1500 milliampere hour battery, if you're going to draw 100 milliamperes, it will last you 15 hours. Very simple, because it has to deliver power at 3.7 volts. So that's the norm. If you draw more current, it's going to last less. Okay, very, very simple method. But it's good to know how much power your phone actually consumes. So if you look at your battery, your what is the milliampere hours, and then look at your phone specification. So maybe it says for GSM your talk time is 14 hours. So what does that mean? You take your battery capacity, divide by the number of hours that is specified for talk time. That is the current that you are drawing during talk time. Milliampere hours divided by hours is the milliamperes that you are drawing. Multiplied by 3.7, that's the power your phone is consuming when it is in talk time. That means it is actively transmitting. Okay. On the other hand, if you were in standby, that means you are just connected to the network but not making or receiving phone calls, which means that the standby time would have been specified also. Even some 10 years back, the talk time was the standby time was already 25 days. 25 days, 600 hours, which means only 8.75 milliwatts of power are being consumed by your phone because it has turned off all the non-essential functions. But good to know how your phone is rated. How much is your talk time? If you're watching videos, what is your battery life? You can basically calculate approximately how much power is being consumed. Now, when we were designing phones and somebody dropped the phone, it was considered, oh, why did you do that? Can't you be more careful? Because what will happen? The battery will come off. But the biggest thing that we were worried about was the display will stop working. And what was there in the display? It was a 4-line display with nothing much, few dot matrix elements. Okay, now move the clock forward 20 years. You have these fancy touch screens, and people drop the phone like that and pick up and say, oh, it's working, no problem. And it's like, wait a minute, do you know what is behind that touch screen phone? It is not just, oh, it's just working. So here is your display. On top of that, there are 2 layers which actually form a matrix of connections. Okay? And then after that, there are several layers of bonding, and then finally a protective layer. So now when you touch a point, what it generates using this grid is a region of locations where the contact gets made. So it says, okay, this is approximately where the person touched. And then it is given to some signal processing device, which then narrows it down and says, okay, here's the center of gravity or center of the location where the person has touched, and finally figures out exactly the coordinates of the point that you touched. And just being able to touch, shrink, and expand, it is amazing amount of signal processing that's going on with an amazing amount of electronic that's sitting behind it. And you just threw the phone on the ground, and it's like, show more respect to the phone, because it is one of those amazing devices. So this is the fact that you can drop a phone, pick it up, and expect it to work. is actually one of the amazing feats of cellular engineering, because in the olden days you drop the phone, it's probably going back for repair because the display would stop working. Okay, any questions? Hopefully something you heard which was not something, maybe something that was new.
Telescopic antenna,
Okay.
how they receive the call? Because the antenna will be
Okay, that's a very, very good question. How did the telescopic antennas receive the call? Because you don't know when a call is, when you're making a call, you extend that. Okay. Now, between an antenna that is extended and an antenna that is in its compact position, there is a difference of gain. So that, let us say, is 4 dB, is a difference in gain between what you would have if you had a telescopic antenna. So the signaling channel, the channel that tells you that a call is coming in, has got 4 dB more link margin than the voice channel. So even though the antenna is down, the signaling channel will still get through because it has got 4 dB additional link margin, so that your phone, even with the antenna being down, will still know that a call is coming in. But the minute you are alerted by means of the ringing, the first thing that you will do is extend the telescopic antenna so that you can then speak on the phone. But good question. Good, it's a system level question. It's a good to know how the system works. Any other question?
You said this, in the given example, you said this Madras database and the Bangalore database. So, is the communication wireless or wired?
Wired. Oh, all signaling other than the communication between the mobile and the base station, everything else is wired. So it's basically a complete wired telecommunication network with wireless access. Only the access part is wireless. Everything else is wired, and it's mostly optical. It's very, very high speed communication links.
There has to be a communication between two different operators.
Yes.
Instead of Vodafone from Chennai based to Vodafone to Bangalore based.
Yes.
So, is there any other module in the middle?
No, basically there is a signaling scheme which, because the Vodafone gateway will talk to the Airtel gateway. So the gateways have a protocol by which they can communicate. Different gateways of different. You cannot talk directly to the switch of the another operator. You can only talk through the gateway. So basically, the gateways have a protocol. Okay. The question was, can you? How do they different operators' networks talk to each other?
So what effect takes place if we had a 0 bit before the 10-digit number? So suppose we connect to Bangalore and
Yeah.
we connect to Chennai.
Yeah.
Like what's the difference between?
Okay, so basically it is how your landline network or mobile network recognizes and interprets the 0. So in most cases, a 0 may be just ignored or just be told that, okay, this is an ISD or STD call. But at the end of the day, it will still look for the number that has been dialed, because that number basically has to be clarified with the local database, because they need to know where to route your call. So though they assume, the local network assumes that, okay, this person is trying to dial an ISD call, STD call, but they will still look for parsing the number and trying to understand. So that's why even if you dial +91, it will still take the mobile number, and then that's what is processed. Okay.
Is the protocol same for voice over LTE?
No. Voice over LTE is a packet system. So the entire mechanism by which you connect to another user is completely different, because it is like the internet. So both users are already connected to the network. The assumption is that all you're triggering is an application that will connect the two of you. You are not signaling to the other user and saying, okay, where are you, how to find out. This is for a circuit switch call.
There were two 4G standards, WiMAX and LTE.
Okay.
What happened to WiMAX?
Okay, very good question. At one point, it seemed like there were two very, very strong contenders for the 4G space. The contenders were coming from, one was coming from the cellular dimension, that was the LTE. The other contender was coming from fixed wireless. Basically, WiMAX was a fixed point-to-point or point-to-multipoint communication link, to which they added mobility. So the question is, which one is more adapted to the requirements of 4G? Do you take a cellular network and migrate it, or do you take a system that is primarily designed as a fixed system and give it mobility? Both had similar features, but because the cellular system already had maybe 4 billion plus subscribers, more people went on to the cellular side, and market forces more or less were in favor of LTE. But there was a fundamental difference. One was a cellular migration, the other one was adding mobility to a fixed system, which was difficult, but it was done very nicely. Okay, excellent. Keep asking those questions. Now the question is, I don't even have 4G on my phone. I am actually using 2G. Why are you talking about 5G? So I think it's a very valid question. Let's see if we can give a reasonable answer to this question. Next slide is actually quite an interesting slide, very important one. 60 seconds. Look at your clock. 60 seconds. In 60 seconds, this is how much information has flowed across the internet. 5 million videos viewed on YouTube by different people, of course, and about 293,000 Facebook status updates, 138 million emails, 67,000 photos uploaded on Instagram, and the list goes on. You can see this list, and it's a sum of all this. Okay, all of these are happening within 60 seconds. Now, if you assume that countries like India will have a significant portion of this as the internet traffic that we are generating, and for us the only way we can access the internet or broadband will be through wireless, then you already have the answer, because today's 4G can do all the voice. It can do quite a good number of data applications, but nowhere near the type of capacity that you will need for this level of information flow. Now, this is flowing on a wired internet, but for countries like India, our portion of this data will have to go on a wireless network, which is why we are looking at even talking about 5G. 5G is very, very important for India, because this is the reality of the situation. So now the question is, okay, I throw away 2G, 3G, 4G, and then I bring in a new system, 5G. No, the answer is not that. 5G is probably going to be a superset or an integration of all the features, because we know that markets like India, GSM is not going to go away. There will be pockets where GSM is there, 3G will be there, 4G. And of course, we know that Wi-Fi is an important technology. Why not integrate that also into 5G? So in terms of these technologies, it's not necessarily a brand new technology, though there could be a new system called 5G, but it is by and large going to be integration of old ones, possibly some new technologies coming in as well. Why new technologies? Because we already talked about the number of applications that will require broadband. And a lot of these applications are machine to machine. So therefore, when we talk about connectivity of things, called Internet of Things, connectivity of devices, there's a lot more machines that need to be connected to each other, connected to humans. This is going to require additional types of communications, and all of this has to be done with energy efficiency. Remember, green communications. We also recognize that a lot of the applications will be inside of buildings. So therefore, our wireless coverage inside buildings must be improved very, very significantly. M-commerce is going to be very significant in the future, and location-based services, and of course new applications like people watching high-definition videos on their handsets. So again, there is a whole spectrum of potential applications, and also a recognition that the only way we can do this is something very, very efficient. That's why 5G is being talked about. So this is one of the slides that you may have to tell me whether it's readable, but let me just highlight the fact that there are applications that require very high speed, like high definition television. There are scenarios where you would have to connect thousands of devices. Let us say you want to do meter reading across the city of Chennai, electricity meter reading. So there are thousands of these devices that need to be connected, but the data rates are very small, maybe 100 bits per second, but the numbers are very large. Spectrum. We don't have a single spectrum, but we've got some spectrum in 900, some in 1800, some in 2.3 gigahertz. So basically the spectrum is fragmented, so you must be very flexible. The latency, if you want to have control of a traffic signal, using wireless mechanism, basically smart transport, city-wide transport, which means that your ability to control the traffic signal must be very precise. So that is low latency. You cannot send a command and then it responds after 5 seconds. So basically there are scenarios where you must have very, very reliable, very low latency communications. And of course the whole issue of mobility. So here are the different dimensions. Cost is important. If you are putting up meter reading or some all the vending machines have a device to report back their current stock, those will require long battery life. You don't want to keep having to go and change the battery. Some applications demand very high reliability, and then there are of course issues of security. So how do you meet these requirements across with a solution? So you can see that flavors of 5G will be such that you may have the dark blue communications, which is geared towards machine type communications, low latency, low data rate. Then there are this light blue, which is what we call mission critical, police communications, traffic signal control, the automated factory. Those are mission critical. You have to be very, very low latency. And then of course the medium blue, which is talking about your very high data rates. So again, different flavors, there will be options for us to solve these requirements using the different systems that we have. Okay? Let me leave you with the slogan of 5G, and it sort of tells you how to think about 5G. 2G, when cellular systems came in, 2G, they said, anywhere, anytime, you can connect to anyone. Okay? Anywhere, anytime, anyone. That's what 2G promised. Okay? You pick up the phone and you call. 5G says everyone, everywhere, everything, devices also, always connected. You don't have to connect them. They're already connected. That's 5G. So how do you maintain the connectivity? How do you manage the mobility? That's part of the challenge that we see. Okay? 5G, they also say that you must give the user perception of infinite capacity. So they should not worry about, okay, am I ordering a pizza or am I going to watch a movie? That doesn't matter. The data rate will be sufficient for the application that you are looking at. Okay, so this is how 5G will be viewed, and it more or less tells us how we should look at the evolution of cellular systems. It's not just that a few people who are very fascinated with technology think that we should now come up with 5G, or it's just a buzzword. No, it's not a buzzword. The market forces are driving such that 4G may soon run out of the ability to support the market opportunity. So that's why new systems will come, and that will be called as 5G. Okay, any questions?
So 5G will basically be using the same spectrum as
Well, the question regarding spectrum is coming up in a later slide that will be addressed tomorrow. The answer is it can use existing spectrum, but most likely it will be deployed in new spectrum. And the reason is a 2G system and a 5G system may be difficult to coexist in the same spectrum. So what you would have to do is something called spectral refarming. That means today you have GSM, you have to clear it. Just like a farmer says, okay, I'm going to plant a new crop, refarming. Okay, now it's no longer groundnuts, I'm going to grow rice. So basically you clear out all the GSM and you have to deploy 5G or 4G. So refarming is difficult because already operators have got equipment, so they prefer to use newer spectrum. But somebody like Reliance Jio, who doesn't have 2G, 3G, comes in, they can deploy wherever they have spectrum, they can deploy it. Okay. Okay. Yeah.
For IoT, why can't we use Wi-Fi instead of going for 5G?
Yes, very good question. And the answer comes from the business people. If you tell the cellular industry saying, you know what, you already got 6 billion subscribers. Why don't you be satisfied with that? Why do you want to go after one more market which has got only 20 billion subscriptions? They'll say, no, 6 billion is good, another 20 billion even better. So it's market forces. Right? So of course, if they were so cooperative, they say, okay, you take voice, I'll take data. No, they don't do that. Everybody wants, because it's a large market, everybody says, Bluetooth, your job was to connect headsets and music players. Why do you want to go into IoT space? Because they say it's a big market, let me go there. It's market forces. So basically the markets are huge and each one is leveraging their own strengths. Cellular says, hey, the minute you give me your traffic, everything is taken care of. Mobility, authentication, billing, everything is taken care of. If you go to Bluetooth, he has no way of billing the system. You have Wi-Fi, there's no mobility. Whereas Bluetooth says, hey, I can last 10 times longer than the cellular phone. Why not you give me the business? So there are market forces that are in play. Okay, what I want to do in the couple of minutes that are remaining is to show you the computer assignment and encourage you to start thinking about it. The TAs and I will be happy to help you. Basically the goal is to verify the theoretical bit error rate performance of a QPSK system. Okay. So the way you would do it in a conventional sense is you would generate bits, modulate it using QPSK, add some pulse shaping, noise, and then you would pass it through a match filter, demod, and then compute the bit error rate. That's what is supposed to be. But if I tell you 10 dB EB by N naught, get me the bit error rate. It's actually very, very difficult. Why? Because where do I measure EB by N naught? I don't know. Because N naught is what? Noise spectral density, watts per hertz. And do I measure it before the filter or after the filter? I have to measure it before the filter because it's not N naught is not constrained by whether you used a square root raised cosine or a Gaussian filter, does not matter. So actually if you see, EB by N naught is not a quantity that is easy for us to understand and work with as a practical engineer. What you can do is what is called carrier to noise ratio, the power. So basically you put a power meter on the signal side, you put a power meter on the noise side, and then you say, okay, this ratio is carrier to noise ratio. That I can measure, that I can control. But now how is this linked to the EB by N naught? That's a very important question. That is one of the things that this assignment will help us understand. Now where do I measure signal to noise ratio? Not in the air. After I have passed through my receive filter. So after I have passed through my receive filter is at this point, right, where you can see the marker there. So can you see the marker there? That's where you, but by that time signal and noise have already mixed. There's no way I can measure signal alone and noise alone. How do you do signal to noise ratio? Okay, some very, very interesting questions. Think about it. In the next class we'll spend a few minutes to explain how it can be done in a very systematic way. 10 dB EB by N naught will give you 10 dB EB by N naught, and the bit error rate will be exactly what Proekis and other books will prescribe. You can verify it. So that's part of the task. It also tells us what's the role of pulse shaping, how do I do upsampling, downsampling, all of that is also needed because if you want to talk about synchronization and others, but it's a basic experiment, but it will probably teach us a lot of things on which we can build. Take out this channel and then add a fading channel. That's what we want to do, but we need to have this baseline. That's what we will do. Okay, thank you. We'll pick it up tomorrow at 8 o'clock. Thank you.